Good morning, students. I'm sad I can't be there today. I'm sure you guys are all looking spry as usual. Um, Hopefully, you have a great morning so far, and hopefully, this video will serve to lighten your mood. Today, we are going to do a lab. Hopefully, before you watch any more of this video, please make sure that you have a lab sheet on it. Okay, one of the first pages is me going through the example on the front page. This is me going through the example on the front page. So make sure that you follow along with me on that front page as we go through this example. You should be able to get a feel of what we're going to do today in the lab if you follow along appropriately. Okay, every part of this lab, there's 5 of them. Okay, they shouldn't take very long, so don't freak out that 5 is a lot. Okay, it shouldn't take very long, but if you pay attention in the next, however long it takes for me to record this video, because I'm a one shot take kind of guy. I mean, that's how I do it in the classroom. So why should I waste all my time doing a bunch of recording when I can just do it once and mess up? And it's okay because I trust you guys. You guys can make fun of me. I don't care. Okay, so follow along. There's 3 questions in each part. Okay, the 3 questions are: is the box in equilibrium? We're going to talk about that. Is there a net force? If so, which direction is the net force, and how do you know that direction? We're going to talk about that as well. And number 3 is draw a free body diagram of the object, labeling all the forces. Okay, that might not make any sense right now, but after this example, I'm sure it'll make sense. Okay, so here's what we're going to do. As you see, the scenario for Mr. Derry's example is a box being pulled up a ramp with friction. Okay, so if there's a box, in this case, here's my box, right? I have a box, I'm pulling it up a ramp, it has some sort of friction. Okay, what we want to do is we want to draw, that's the end goal, is to draw a free body diagram of this box. Okay, that models the forces involved on this box. Okay, and the reason why I do this example is because it's going to be the most complex example, so hopefully you'll have more than you need to do the easier ones. Okay, so first thing, if we pull this box up, is the box in equilibrium? Well, if I pull with a constant force, we know it is, but let's just say that I don't, and I, kind of pull it quickly. Okay, it has some sort of initial acceleration. We know that if there is an acceleration, that there is a net force. Okay, so in that first question, in that first box, or in that first question in the Mr. Derry's example, is the box in equilibrium? I would say no, because I am accelerating the box as I pull upwards. Again, if I gave a nice even pull so that the motion doesn't change except for at the beginning, then I don't have a net force because it's in equilibrium and there's no acceleration. No acceleration, no net force. So when you're doing these examples, think, is my car, or is my, mostly you're doing with these cars, is my car speeding up or slowing down? If it's speeding up or slowing down, that means there's a net force somewhere. If it's slowing down, the net force is in the opposite direction of the motion. If it's speeding up, then the net force is in the direction of the motion, right? So, is this box in equilibrium? The answer, no. Okay. Is there a net force? Yes. Well, which direction? It says, if so, which direction is the net force? And how do you know? Well, if we're accelerating in the direction of the motion, okay, that means the force is in the direction of the motion, right? So, is there a net force? Question 2, yes. If so, which direction is the net force? We're going to say, from your perspective to, the right of the box, or toward the books, you could say, up the ramp. All of those things are a proper way of giving direction into where is the net force on this box, okay? And how do you know? Well, the box is accelerating in this direction, okay? If I were to increase this and let it fall, it accelerates downwards. In that case, the net force would actually be down the ramp, okay, because it's accelerating downwards. Gravity is taking over at that point, okay? So, I don't need that box anymore, so I'm not going to even pick it up, okay? Here's the most important part, okay, is your free body diagrams. Pay attention closely. I'm going to make sure that we get this well, okay? So, part 3, okay, well, question 3 of this part of Mr. Jerry's example is we need to draw a free body diagram of the block on this ramp, okay? So what do? Easy. All we got to do, okay, is make the table, make the ramp. You can even draw the books if you want, okay? It's on top of something. And then we'll draw the box. Okay? It has some force, okay, right? We're free body diagram, we want to label the forces. We're going to have a force downwards, okay? Even though this ramp is at an angle, gravity still pulls down, okay? It's not like we're standing on the earth like this, right? Gravity's still down. So we're going to keep the force of gravity, Fg, force, gravity, down, right? What's some other forces that we have? Well, we have the force of gravity down. We also have the force, the normal force, right? The force that the ramp is putting on the box, okay? That's going to be perpendicular, okay, to the ramp. Because even though the force of gravity is this way, the force normal is still this way. Because the ramp is angled, so therefore the normal force is angled. We have the force of the string, okay, or the force applied, going in that direction. And then lastly, we have the force of friction. That is propelling the motion of the object, wanting to kind of keep it down. So these are our 4 forces involved. Now, when you get to high school, if you take physics with me again, you'll learn to actually use these forces for something. But for the sake of this lab, you don't even need to put numbers on any of them. All I need to know is can you recognize the forces and them involved and where they're at. The other thing to note is remember that these vectors, they symbolize the magnitude by the length, okay? So if there is a net force in a certain direction, make sure that you kind of make it clear that there is, in fact, a larger force in that direction than in this direction, okay? These are relatively the same. Now, the angles make it a little bit tricky, but it's close enough. You'll have one example where you will have it on a slope, and this is what I want you to kind of match with that, okay? So that's basically what you'll do 5 times, but you're going to change up the situation each time. Okay, the first time it's just a car, your little car on a table. Just set it there and look at it. Okay, is the object in equilibrium? Is there a net force? If so, which direction is it in, and how do you know? And then draw a free body diagram labeling the forces that are involved. Okay, next one. Gently push the car forward and let it go. Okay, this will likely have to be done on the ground somewhere, in the classroom, in the hallway, doesn't matter. Okay, make sure you are where your sub knows where you are. Okay, don't freak her out, be good to her. And that's part 2, answer the same exact questions. Part 3 is a little bit interesting. You'll take your car, okay, you know where to find these. To the drawer right to the right of them, you'll find some string. I think I might leave some string with the teacher as well. So if you can get that string, most of your cars have this little nub at the top, right? What I want you to do is I want you to tie a string around that, and I want you to pull it behind you, like one of those old toys that maybe you used to play with, where you would drag it behind you where it's on the floor, okay? This way we get a force being applied to it at an angle. Okay, because I want you to see how a force applied at an angle is labeled on a free body diagram. Okay, so that's part 3. Tie a string, pull it behind you, with it on the floor, and you kind of walking. Okay, one person can do this. That'd be great. If you want to take a picture of it and submit that on Canvas, that would be fun. I would enjoy that, but you don't have to. That's part 3. Part 4 is basically the same as part 2, but what I want you to do, instead of pushing it on the tiles, I want you to push it on something more rough, okay? So the example is like carpet, sandpaper, or a towel. If you have sandpaper, great. You could probably use maybe the kind of dry erase towels, marker board towels, if you wanted, or if you want to try to find some carpet somewhere in the school, that would be great. If not, if that one doesn't really work out for you guys, you can maybe skip it and that'd be okay. And then the fourth or the fifth one, sorry, is we're gonna roll it down the ramp, roll it down the slope that goes into the commons area. Okay, so don't push it, just kind of set it and let it happen. Okay, you know that these guys can go very far. So what we need to do is we need to have someone on the opposite end ready to catch it. Okay, because we don't want these crashing. We don't want these going at light speed. Okay, just let it go down. Draw a free body diagram of that. What forces are involved in that? It's very similar to this. I'll say this, but instead of the force applied being the one that takes over, you're probably not going to have a force applied. Instead, you're going to have a force of gravity that's much stronger going down, and that y component, that x, this component this way, is going to pull it down. So it's going to look pretty similar to this. If you don't get that far, that's okay. I purposely on my labs give you a lot to work with so that you're never kind of wandering around trying to figure out what you're supposed to do, right? If you are done early, please check your grades, make sure that everything is up to par. GimKit tomorrow, you can find that on Canvas. I hope you guys have a great day. I will miss hanging out with you and seeing all your lovely faces, but I probably won't miss you that much because I'm going to be hanging out in Texas with my cousins and probably eating some really good food. And as a certified big back, that excites me a lot. Okay? Have a great and wonderful day. I'll see you guys on Monday.